Okay, so Michael, let's see if we can do something that might be faster and just as good as what we've been doing with value iterations. And what we're going to do is we're going to emphasize the fact that we care about policies and not values. Now, it's true that given the true utilities, we can find a policy, but maybe we don't have to find the true utilities in order to find the optimal policy. So here's a little sketch of an algorithm, okay? So it's going to look a lot like value iteration. We are going to start with some initial policy. Let's call it pi sub 0. And that's just going to be a guess. So it's just going to be an arbitrary setting of actions that you should take in different states. Then we're going to evaluate how good that policy is. And the way we're going to evaluate it at time t is to calculate its utility, which I'm going to call u sub t, which is equal to the utility you get by following that policy. Okay? And I'll show you in a moment exactly how you do that. All right? Okay. But I just want to make certain that you kind of buy that maybe we could do that. So we have, given a policy, we ought to be able to evaluate it by figuring out what the utility of that policy is. And again, we'll talk about that in a second. And then after we know what the utility of that policy is, we're actually going to improve that policy in a way similar to what we did with value iteration. We're going to update our policy time t plus 1 to be the policy that takes the actions that maximizes the expected utility based on what we just calculated for pi sub t. Now, notice that will allow us to change pi over time, because imagine that we discover in some state that actually there's an action that's very good in that state that gets you someplace really nice, gives you a really big reward, and then that point on you do fairly well. Well, then all other states that can reach that state might end up taking a different action than they did before, because now the best action would be to move towards that state. So these two steps will actually, or can actually, lead to some improvement of the policy over time. But the key thing here is we have to figure out exactly how to compute u sub t. Well, the good news is we know how to do that, and it's actually pretty easy, and it boils down to our favorite equation, Bellman's equation. So our utility at time t, that is the utility that we get by following the policy at time t, is just, well, the true reward that we're going to get by entering that state plus gamma times the expected utility, which now looks like this. There, does that make sense? Do you see that?
Okay, wait, hang on. It looks a little different from the other equation. So did you mean for it to have ut is defined in terms of ut and not ut minus 1?
Yes.
Okay, that's interesting. And the max is gone, but instead of a max, there's a policy stuck into the transition function, right?
Yep.
The choice of action is determined by the policy.
Right. And that's actually the only difference between what we were doing before, is that rather than having this max over actions, we already know what action we're going to take. It's determined by the policy we're currently following.
Okay, but isn't this just as hard as solving the thing with the max, you said?
Well, what was the problem that we were solving before with the max?
That was the Bellman equation.
Yes, but we were solving a bunch of equations. How many of them?
N.
So we were solving n equations, and how many unknowns?
N.
What's the difference between this n equations and n unknowns and the other n equations and n unknowns?
Well, n is the same.
Mm-hmm.
There's no max, though.
There's no max. And what was it that made solving that hard before?
The max made it nonlinear. The max is gone now. Are you saying this is a set of linear equations?
Yeah, because, well, it's just a bunch of sums, and the pi is not like some weird function. This is just effectively a constant.
I see.
So now I have n equations and n unknowns, but it's in linear equations. And now that I have n linear equations and n unknowns, I can actually compute this in a reasonable amount of time by doing matrix inversions and regression and other magic hand-wavy things.
That's very slick. It seems it's still more expensive than doing the value iteration update, I guess.
Yeah, but you don't have to perhaps do as many iterations as you were doing before. So once you've evaluated it, which we now know how to do, and you've improved it, you just keep doing that until your policy doesn't change.
Very cool.
Mm-hmm. And this does look a lot like value iteration to you, doesn't it?
Yeah, though it seems like it's making bigger jumps somehow.
It is, and that's because instead of making jumps in value space, it's making jumps in policy space, which is why we call this class of algorithms policy iteration.
Cool.
Right. Now, this inversion can still be fairly painful. It's, if we don't worry about being highly efficient, it's roughly n cubed. And if there are a lot of states, this can be kind of painful. But it turns out there's little tricks you can do, like do a little step of value iteration here for a while to get an estimate, and then kind of cycle through. So there's all kinds of clever things you might want to do, but at a high level, without worrying about the details of constants, this general process of moving through policy space and taking advantage of the fact that by picking a specific policy, you're able to turn your nonlinear equations into linear equations, turns out to often to be very helpful.
So is it guaranteed to converge?
Yes.
Nice.
Well, that was easy. I'm not going to go into it, but there's a finite number of policies. You're always getting better, so eventually you have to converge. It's very similar to or at least intuitively, it's very similar to the argument you might make for k-means.
Cool.